Okay. Yeah, I think the recording is on. My screen is visible. I hope I am audible to you guys as well. So let's begin with the discussion session for week 9. Okay. Last week we had covered till the point where we had defined function approximation, how we can use a kind of linear parameterization in order to define the uh, value function approximation and how the data can be manipulated and represented in such ways. And then we also looked at how function approximation works with eligibility traces. We have seen the control part of it. And lastly, I think for the last 10 minutes, we looked at the state aggregation methods, right? So we'll continue where we left off. So we'll start with an algorithm called LSTD. LSTD stands for least square temporal difference method. Least squared temporal difference. Okay, let me color this. So the basic idea when we say something is a least square method, what we do is, let's say there is an optimal value function, there is an optimum value function that one needs to achieve or one tries to achieve, and there's a predicted or an approximate value function or an estimated value function that we somehow arrive at, right? So we want to figure out how close we are to that particular value function, similar to how your mean squared error function works, right? So you take the uh, difference between them, you square it up, and you would try to minimize that particular thing. So this thing takes, so this algorithm takes that particular idea into account, and uh, the algorithm works in the following way. Okay, so firstly, we need to understand that all states that we have needs to be mapped to a phi representation. Okay, that means phi is some kind of parameter that contains the essential information of a given state, which is fed into the regression model to generate the target or the appropriate value functions. Okay, so let's say, assuming I have n number of states. Okay, assuming I have n states. Okay, so my value function for this particular case, so my value function belongs to the space of R of n. Okay, similarly, so this is the state representation. Okay, if I have n states, the value function is uh, belonging to the space R of n. Similarly, my phi representation, which is the parameterized form of representation, belongs to the space of Rk, R, R of k, with the assumption that my k is much, much smaller than n. Okay, meaning the dimensionality of the parameterized representation of of a state is much, much lesser than the amount or the number of or the original dimensionality of the state spaces. Okay, so if I were to represent it, let's say we use a different color here. So say this is my phi space. Okay, this is the space for my parameterized representation. So this here phi, in this case, k is equal to 2 because uh, so phi is sorry, phi has is a 2D representation, and my total space is R3. Okay, because beyond that I won't be able to show it on this paper over here, right? So let's say for a particular state, my value function that I get or a value function that I start with, uh, assuming this is the value function that is the optimum value function, okay, for a particular state S, this is the optimal value function, okay. Now, since I have to represent my state in the uh, phi space, so I need to take a projection of I need to take a projection of it into the phi space, right? So if this represents the vector for my value function v of pi, I can define my projection as this quantity over here, which we'll call it as v optimal, v opt. Okay, this is the optimal value function that one can achieve if one is operating in the p space. Okay, and say we start with some arbitrary value function initialization. We start with some arbitrary v naught, then we keep on operating the Bellman operator, and the idea is that if the Bellman operator is operated a sufficiently higher number of times, one would eventually converge to the fixed point, which in this case should ideally be the v op. But in practice, you don't really reach v op because for that you need to perform the iterations for a very very long number of steps. Ideally, you don't reach v op, but let's say you reach some optimum near v opt. Okay, so let's say this is if we reach within some optimum value with that, we say that we have converged, and we'll call it as our v hat of star. Okay, so this is basically the optimum function that one would like to reach. Okay, so the way you start is you first define some arbitrary v naught in the phi space. Okay, so you start with some arbitrary v naught. This is v hat naught. Okay, because I'm starting with some estimate, right? Let's say this is my v hat naught. Okay, this point over here. So on that v hat naught, I operate some contraction operation. Okay, so my contraction operator looks like this. So I operate this on v hat naught, I should get v1. Okay, so you can think of it like this. You operate the contraction operation, you get mapped to some value called v1. Okay, but again, this mapping that you have done is in the uh, original state space dimensionality. So you again need to project it back to the phi space. So you project it back here, and then you get your v1 hat. Okay. So once you get v1, so in order to make it into v1 hat, that is, in order to make that particular projection, I need to apply some projection operation, right? So there is a projection operator also being applied to v hat naught. Okay. So this is the uh, composition of operation that one needs to apply in order to complete one iteration in order to reach closer to the goal. And this is in the phi s state parameterization or the state representation that we are looking at. Okay, so you do this continuously, and eventually you should reach your v hat of star. Okay, your estimated optimal value function that you can uh, obtain from this. Okay, and how exactly one works with that? So this is the basic idea behind the LSTD algorithm. Now, uh, how the data looks like. Okay, let's say you're sampling data and you want to pass it through a regression model, right? So your data looks like this. So typically, when you run a regression model in classical ML, your data is of the form x1, x2, dot x. So let's say this is one particular input, and for that particular input, you get an output of y. You collect, you call it several such data sets, then you pass it through a regression, and eventually you should get some f hat of x, right? So this is how your classical regression works in ML. In RL, the data looks somewhat different because in RL you don't typically get a data set. You then get an input and a corresponding labeled output, right? So in RL you have a trajectory. So let's say you have some initial start S naught, then you take action A naught, you get reward R1, then S1, A1, R2, something like that. You have a bunch of trajectory when you define the MDP, right? So this is how your data looks like. So from this, I need to be able to make into some data that could go into my regression model, right? So this is typically how the data looks. So I first, for each individual state, I first represent it into its parameterized state. So let's say this is phi 1s, phi 2s, dot dot dot, phi k of s. Okay, so this is a vector for that particular state, and the output would be the value function for that particular state. Okay, so this is how my uh, data should look like for an RL problem. And how do we estimate the value function? The value function is estimated as my value function v of s here would be, let's say we are looking at just the linear parameterization. So it's simply my phi transpose of s times theta. Okay, where theta is the weights of the polynomial or the neural network, whatever regression model you are employing. Okay, so if this is clear, now just I want you to recollect this particular formulation, what happened in LSTD. We first take initial V naught, we apply the contraction operation for an MDP problem, could be a Bellman operation or any other contraction operation that you can apply to it. It gets the output is projected in the n space. We want to project it down to the phi space or the dimensionality of the phi space, which is of dimension k. So you define a projection operator. And so basically, this projection operator tells me the distance between these two quantities, right? The distance between my v1 and my v1 hat. Okay, so we want to be able to minimize that particular thing so as to reduce the error in the measurement. Okay, so that's why the name comes least square TD method. Now, assuming that the particular method that I have mentioned, since it's a contraction operator, and assuming that we are operating on the Banach space, I say that my v pi hat is a fixed point. Okay, for this particular operation, for this particular contraction operation, my v pi hat is a fixed space. Okay, and once I say that, I can figure out the solution, right? So since v pi is a vector, I can uh, unroll it out. I'll have n equations for n variables, and I can solve it to get the solution for v pi, right? So the solution for v pi looks like you have r pi plus gamma v pi v hat v pi. Okay, v pi v hat pi. What I've done, I've just operated the contraction operation here. Here in this case, it's the Bellman operation that I've applied. On top of that, I need to apply the projection operation, right? So the projection operation looks like this. So I have quantity. Okay, so all I've done is I've just written down the explicit matrix form for the corresponding operators defined above. Okay, I just flipped the LHS into RHS, and this is how I wrote it down. So similarly, for my Q function, I can, let me not write it. Okay, times, we get this quantity, copy, paste. The only difference is here, instead of v pi, I put my q pi, right? Q pi, right? So this is how my two equations look like for LS3D. Okay, but what could be an issue in such cases, right? First is that we need to uh, first fix a policy pi. Okay, then we need to know the transition probabilities, which is p pi. We also need to have an idea about the rewards that are available. So we need to have a knowledge of the reward distribution. Okay, so containing that particular knowledge again leads to the part where we had to use dynamic programming. Okay, but since so far we have come where we have employed Monte Carlo and TD methods, which is a sample based method. Complete knowledge of the state is not necessary. We should be able to simply sample certain trajectories, sample certain experiences, and make updates. But knowledge of the transition function requires a complete knowledge of the state, right? So how do we define that? Okay. So in this case, what I'll do is remember this. This is how my linear parameterization of Vs look like. Okay. So I just take my V pi equation and substitute that particular equation that I just highlighted over here. So I get 5 times theta pi. Okay, this is the matrix representation, so the transpose goes away. Okay, is equals to. I just copy this big equation, this quantity plus I copy this quantity as well. Okay, and here also I should replace my v pi with 5 times theta pi. Okay, now I have to find the solution for theta pi. Okay, so I bring all the theta pi's to the left hand side and take everything else to the right hand side. So what I end up getting is I have theta pi is equal to phi transpose phi minus gamma p pi phi inverse phi transpose r pi. Okay, you can obtain it by you know uh, doing some algebraic manipulations. You just take all thetas to the left hand side. Okay, you will get this equation. Okay, so let me color this. This is an important result. Uh, but still, I have to remove the dependencies of R pi and uh, P pi, right? Specifically P pi dependency that I want to remove. This is the transition probability. Okay, so I can write this as, so here instead of taking some kind of a weighted, some sort of, say, sample averages, I need to take a weighted average of sorts, right? So what I do is, in both cases, I take this quantity, I add a weighted parameter W, which is apparently acts as the weightage for how many times that particular state is visited, times theta minus gamma p pi theta 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 pi is equal to theta transpose again w times r pi. Okay, what I've done is I've taken this quantity here, which is the inverse, to the left hand side, so it no longer remains the inverse. Basically, I have just multiplied this quantity on the LHS and the RHS and have added a weighted term. Okay, so each time a particular state is visited, the updates that I make isn't just a sample average, but a more of a weighted average. Okay, so I color this as well. Okay, and I'll call this here equation 1. Okay, now notice here equation 1 is of the form a theta pi is equal to b. Okay, if you look closely, this is equation 1 is of the form a times theta pi is equal to b, where my a is my a is phi transpose omega, sorry, w theta minus gamma p pi phi. Okay, so this is how my a looks like. So if I write it in the vector representation, so this is how it should look. So it's the sum over all states phi s ws times phi s minus gamma, and this is the p pi matrix, right? So here this is the probability of state, action, and the next state. Okay, but here since we are fixing a policy pi, my action is not a but rather pi of s. Okay, times remaining phi s prime term, right? The whole transpose. Okay, so this is done because I have written it in the vector notation. Okay, now what I'll do is I will take this. I can write it in this way as well. So what I'll do is, so what I'm trying to do is now what I'll do is I'll take this phi s term inside the bracket term and see how it looks. Okay, so if I try to do that, so it will become clear why I'm trying to do this. So I take sum over all s, this quantity s prime p s pi s s prime times I have phi of s times phi of s minus gamma times phi of s prime, the whole transpose. Okay, and this whole transpose. Okay, so I have taken the phi s term inside, outside, inside, and I have taken this probability term outside. So here the first term, it simply becomes 1 because there is no summation over s prime, only the probabilities get summed up and it becomes 1. The second term remains that. So if you look at the two cases, you can establish the equivalence between these two methods, right? Now what we'll do is, so this is the uh, probability method. This is, you can think of it as an expectation over something, right? So you have a probability of sampling something, and once you do that sufficiently large number of times, you can estimate your a value. So how do we do that? Let's say I have some replay memory available wherein I am storing all the available transitions that I get. Okay, so I am storing SI, SI, AI, RI, S prime of I. Okay, so I'm storing all possible transitions for I goes from 1 to L. Okay, so let's say L is the size of my replay memory wherein I am storing all such transitions. Now all I'm doing is, so whatever transitions that I have stored, so if I have stored L such transitions, I'll simply take the average of 1 by L. This is phi of Si times phi of Si minus gamma times phi of Si prime, the whole transpose. Okay, and this I'll call as my A tilde. So it's an approximation of A. A tilde is an approximation of A. How I am getting it, I don't need to have an idea about the transition probability. If I compute, like collect L transition samples, I can simply draw samples from the environment that the agent is acting on, and I can get this quantity. Okay, so maybe we'll call it number two. So A tilde is a method wherein I can estimate the quantity which is on the LHS without the explicit need of me knowing the transition probability. Even without that, only if I know the phi s representation, the parameterized representation of the state, I can get this transition done. So this is my A tilde representation. Okay. Similarly, now we look at B, small b. My small b looked like this. Okay. So if I write it in the vector notation, I have phi s, omega s, s prime, p s phi s, s prime, r s phi s, s prime. Okay. So this is how it looks. Again, we do the same thing. My uh, we want to put the phi s inside the bracket, and here it's kind of straightforward, right? So I just take this quantity, this quantity, okay, and I put phi. I just put phi s inside, and I get the remaining r phi s s prime term. Okay, cool. Again, I have the replay memory defined, right? So I can define my b tilde as simply 1 by L. I 1 to L. I get phi of Si, and Ri is the sample reward that I get on picking from that distribution. Okay, so this is my B tilde representation. I'll call it equation 3. I'll highlight this. Finally, what we have is my A tilde, sorry, my A tilde of theta phi is equal to B tilde. Okay, now if you notice A tilde and B tilde, you will see that the 1 by L term occurs on both sides. So those gets cancelled out if we substitute it in this equation. Meaning, I know not even, I don't even need to maintain a list or the number of times particular experience has been played. Okay, in order to average it, I can simply sum it up all uh, the experiences that I'm sampling from the that I'm getting from the replay buffer. I just compute this particular quantity and then sum it over all the experiences that I have. Okay, that also makes my life simpler. So such kind of methods is known as LSTD. And since this is done for the value function, this is called LSTD. If it will be done on the Q function, this will be called as LSTDQ. Okay. Next up, we look at an algorithm called fitted queue iteration. So in fitted queue iteration, uh, we want to recover the policy. We want to learn the optimal policy here as well. Earlier, we were only doing the iteration over the value function. Now we want to see how iterating over the value function also helps us, right? So if you remember, recollect value iteration and policy iteration. What happened in value iteration is you keep on iterating the value function until you reach a fixed point. In policy iteration, you uh, iterate your value function for one iteration, then you become greedy with respect to that value function. Then again, you change the value function, you behave greedily with respect to that value function. So your value function and pi both are changing simultaneously. And the convergence, not surprisingly, for the policy iteration was much, much faster than the value function because both are trying to converge to the optimal solution, right? So that helps there as well. So for so this fitted iteration queue iteration method is also called as LSPI. So this is least squared policy iteration. Okay, this also goes inside this. Fine. So for LSPI, uh, the way to recover a policy pi is by being greedy with respect to the queue function, right? So you have argmax of a q hat pi at time t s comma a. Okay, this is how you behave. But my q pi is, if I look at the linear parameterized form, uh, my pi of t plus 1 is simply argmax of phi times theta hat pi t, right? This is how it looks. So here, one obvious problem is how do I take the associated argmax, right? Earlier, for the q function, if I have the q values updated for all state action pairs, I can just behave greedily with respect to the q function to recover the optimal policy if the q function reached the optimal value. Or to simply recover a policy, I need to be just greedy with respect to the current q function that I have, right? So how do I deal with this whenever I want to perform an argmax over my phi times theta hat? Okay, so here, since there is no notion of an action, so there is one way to do it. It's like you define your states to be, let's say this is how your state looks like. So it's sj. So what you do is you take some large number of states, which is from state S1 to Sj. So you take j number of states, or you divide the states into j classes, and correspondingly, you will get your actions corresponding to that particular state. Okay. So what you're trying to do is you're trying to map from a state to an action, right? So let's say you have your uh, state representation. So let's say you have pi 1 s2, let's say phi 1 s1 to phi k s1, and then this corresponds to your action a1. Similarly, you have phi 1 s2 dot 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 phi k of s2. This corresponds to your action a2 dot dot till you get it for some the jth state. So you have phi 1 sj dot 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 to phi k sj, right? And from there you get the corresponding aj. So since you have taken j such classes or j such cases, all you need to do is you need to pass it to a classifier or a regressor. Okay. Depending on the action cases that you have, whether the action cases that you have is a continuous action case or a discrete action case, you pass it accordingly to a classifier or a regressor. Okay, so this is one method in which one can take Argmax, right? So you uh, compute this particular quantity, so my phi times theta hat, you get the corresponding action, and for all such actions, you take the Argmax over that based on the J number of classes that you have. Okay, and the way fitted queue iteration works is similar to how policy iteration work. So you start off with some initial estimate of q hat naught. Okay, you start off with some initial estimate of q hat naught. From this q hat naught, you generate some data. Okay, so the data, how it looks like is you have your corresponding phi si comma ai. Okay, you have that data comma the corresponding uh, q function estimate. Okay, the value function. So your value function is ri plus gamma max of a q hat naught of si prime comma a. Okay, so the target estimation that I make is with respect to the initial q naught that I have over here. Okay, so once I do that, I get some estimate of based on the q naught estimate. I make the update. I get some updated q function. Based on that, I take get the recover the policy and keep doing that until I get to the optimal policy, right? So let's say I do it for m number of times. So let's say I do it for m samples. Okay, in the first round, I take m samples. I generate m sample data. Okay, the data set, right? So maybe I represent it like this. So I generate m such data. I pass it to the uh, I pass it to my regression model where we want to do do this fitting, and from this I get my new updated q function, which will call q1. Okay, after m such sampling, I get q1. From this q1, I'll again generate m samples, wherein I'll take the states with the pi representation. And now the value function estimate that I have, or the q function estimate that I have, will be with respect to the updated q value. So here I'll take q hat 1 si prime comma a. Here also I'll take m such samples. Okay. So from this I'll get q2 hat. Similarly, I generate the data set and so on. Okay, until I reach to the qk hat. Okay, so once I reach, do it k number of times. So once I do it for k number of rounds, whatever q value that I end up with will be the optimum q value, and from that I just recover the policy using the LSPI method. Okay, which is this method, the one I just did. Okay, from this I just recover the uh, uh, policy, right? So this method is known as LSPI, or least squared policy iteration. So I'll just take 1 minute. We'll take a 1 minute break. I'll just get back. Then we'll start with the content of week 9. So far we have covered week 8 content till week 8. Just 1 minute break. I'll be back. We'll start with week 9 content. Okay. Okay, give me 1 second. Okay, I hope my screen is visible. So for week 9, for the content of week 9, uh, we had seen how fitted queue iteration works, right? So the data set that we looked at, the way data set is generated is we have the phi of si comma ai on which is the input, and the target output we'll term as target I. Okay, where my target I is equal to ri plus gamma times max a q hat of si prime comma a. Okay, and here since I want to take a max here, okay, for the target, since I need to take a max over the q estimate that I have for that particular uh, round or for that particular iteration step. So in order to do that, I need to have my training data sufficiently large. My training data, first of all, should be static, okay, in order to avoid the conflict of a moving target. So to achieve stationarity, I'll have a static training data at each round. I'll generate static training data, and my training data should be broad enough to cover all such state action pairs which are present. Okay, so my static training data should be broad enough to cover all S comma A pairs. Okay, only then I'll be able to take a max in this equation over here. Okay, now to make this particular fitting, in order to, uh, I mean, it's always not possible, right? My training data, I mm, I can't always make the assumption that the training data should be broad enough to cover all such state action pairs. If my state space is very large for applications and robotic controls and stuff, if the environment is very large where there are millions and millions of states, then my training data having it cover the entire spectrum of the state space is a difficult task. Okay, so in that sense, what we need to do is one needs to make some kind of an approximation to generate the target. Okay, so one way to do that, one way to approximate the target here, or yeah, one way to approximate that particular the particular q function here. So one needs to make an approximation of the q function, right? So to do that, people make use of something known as a neural fitted queue. So you pass it through a neural network. This is called NFQ. So you pass it through a neural network so that for sufficiently large number of states, you get the corresponding state action data. You generate points so that you can generate your LS data for the least squared, the fitted iteration step, right? So in order to do a max, I need a broad number of state action pairs. And since that doing it by itself is a very arduous task, so we need to have some sort of an approximation to fit the queue function, okay, based on the available data that we have. So you pass it through a neural network, you pass the state action to a neural network, and it should approximate to its appropriate it should approximate the appropriate Q function for that state action pair. Okay. Now, one big issue in this case is, first of all, we remove the issue of a moving target, because here we are always assuming that we have a static training data, meaning at each round, whatever training data that we generate would be static for that particular round. So we remove the issue for the moving data. But one issue that comes up is that we need there is no means to get the phi s comma a representation, right? So that is a big step that is missing in such cases. I need to be able to represent my state action into the corresponding phi si comma ai representation. So in order to do that, people make use of an algorithm of a deep neural network. Okay, so people make use of a deep neural network. So you start with the fitted queue iteration step to estimate the different kind to encompass different kinds of training data. You use a neural fitted queue, but there's an issue with the phi si representation. So in order to deal with that, people make use of a DQN. Okay, DQN stands for Deep Queue Network. So how it works is, you take your particular input, you pass it through a deep neural network. So the way it works is, so let's say I have my input. Okay, I first pass it through a black box, which would generate the corresponding phi representation for that state. This will be neater here. That generates the corresponding phi representation. And from this phi representation, after that, I just estimate the q hat function, right? And this q hat function is the output that I'm interested in. Okay. Notice that whenever I was doing a fitted queue iteration, I always needed to have a data set prepared, and only then I could make an update over that. So in a sense, or yeah, in a sense, it was an offline update that I was making. Okay. What DQN allows me is that I am able to make an online version update to the data set that I'm getting. So I no longer need to have m number of samples, only then I can make an update. I can start making updates as and when I get any uh, experiences from the environment. I get that, I pass it through the DQN model, get the corresponding Q value, make the updates, and move ahead. Okay, so this is uh, an online kind of a method. And since DQN employs Q learning at its core, so it's an off policy. It's an off policy algorithm. Okay. Now what you do is, so uh, for this online computation also, so let's say you have a memory. Okay. In the memory, you are storing your states, actions, rewards, and the next states. Okay. So this is being stored. So what you do is, you keep storing experiences that you gain inside a memory. So let's say this is a memory that I have for I from 1 to L. Okay, I'll call it as D. So in this D could be a stack or a queue, doesn't matter. It's a big data storage chamber wherein I just keep storing the experiences that I get. Okay, from this, if I need to update something, all I need to do is I just uh, take out that particular trajectory that I have, and I just make updates on that. Okay, so it's like a human mind is storing trajectories or sequences of actions in its memory, and when you recollect that, you try to say, okay, this is how I could have improved or so. This is the way human brains analyze stuff on previous experiences. Okay, so this is how this is the idea is taken. So this is known as a replay memory. So you store all the trajectories that you had in the memory, and you replay it to get the updates. This is known as a transition replay. So what you're replaying is the entire trajectories here. But let's say if my state space is still very, very large, okay. So any small changes I made to the state, or it's like if I move from one state to the other, since the state space is very large, the changes to the reward, the actions that I have would be almost negligible. Okay, because since it's a large space, I need to go from one place to the other. So any small step that I take, the action still remains the same. The action reward still remains the same. Okay, because the space is very, very large. So what is done typically in such cases is that uh, in such cases, your state action transitions are more or less correlated, right? So if you keep on sampling from that particular trajectories, there will be a lot of instances wherein the experiences that you have stored would be correlated. So that causes an issue in our case. So here transition replay would cause some issue if we are dealing with large spaces where there are correlated experiences that we have. To get out from that difficulty, so what you do is instead of sampling over the entire trajectory, you replay over, instead of replaying the transition in itself, you try to replay the experiences. So it's called experience replay. What happens in experience replay is uh, I have a big buffer which I mentioned as D. I am storing experiences. Let's say experience, this is experience E1. E1 is the state action reward case. Store E2 and so on. Okay, so I'm just storing it in some buffer memory. And I say that when the buffer memory is up to filled up to a certain height, E of, it's not N, E of M. Okay, this is the maximum capacity of that particular buffer. If it is filled up to that particular point, so instead of using it as a stack, okay, so it's just whatever I have put in first, or a queue, whatever I have put in first, I just make updates in a sequential manner. What I do is instead I randomly sample experiences from this buffer and start making updates to my deep queue network. Okay, so here in this case, instead of taking a particular transition or a particular trajectory, I am sampling random actions. Okay, so let's say this is the particular environment that I have. For simplicity, assume this is a grid world environment. Okay, because it's easier to understand or explain with a grid world environment. So if this grid world was very, very large, uh, this particular state and these four states might have been correlated, because for that particular state, the actions rewards in the next state would have been more or less similar, right? For a large space. Okay. But when I do an experience relay, meaning I sample experiences randomly from the buffer. So let's say uh, in one case, I make updates to this particular state. Okay. Second time, I make update to some other state randomly sampled. Next time, I make update to the other state. Next time to other. So this helps in breaking the correlation ties that one could possibly encounter. Okay. And moreover, this operation or this method is valid. Reason being that my Q learning is inherently an off policy algorithm. Off policy meaning that the policy on which I am estimating and the policy which I am behaving could be two separate entities based on a behavioral based on some other behavioral policy, I can estimate some other trajectory or some other policy that I have. Okay. So because of such advantages and the ease of implementation in such cases, experience replay makes sense for an off policy algorithm and also helps in faster convergence. It uh, implementation wise, it helps in breaking the correlation ties. Okay. So this is the idea behind DQN. Now, what typically happens in a DQN is in Q learning, what you have is for a given state action pair, for a given state, sorry, for a given state action pair, for a given state action, you have a corresponding Q function. Okay. This is from the lookup table that you had for the value function. So for a given state action pair, you have the corresponding Q function for that based on the lookup table. Okay. In DQN, things work a little different. I no longer take in a state action pair. Instead, I feed in a particular state information. I feed in a particular state. My circle is somehow not perfectly today. If I feed in a state information, I pass it through a neural network. Okay. So this is passed through a neural network, which is a black box in this case. We'll call it DQN. From here, the output would be the number of possible actions from that particular state. So this would give me Q of S comma A1, Q of S comma A2, Q of S comma A3, dot dot till Q of S comma AN. Okay, small n. So if from a particular state, I can take n separate actions. So my DQN gives me the corresponding Q function estimate or the Q value estimate for that particular state in picture. Okay. From there, once I get the Q values, all I need to do is I simply need to take a max over that particular. Uh, I need to take a max over that particular state based on the Q learning update rule and make the corresponding updates. Okay, so this is the basic idea behind DQN. But notice one big caveat for DQN. Also, I need to mention that DQN was uh, developed in 2015. The first paper came out in 2015, and this was supposedly the start of a new era in reinforcement learning. Before DQN, reinforcement learning was always treated in a classical manner. After DQN, this paper particularly showed the power of how one can employ deep neural networks successfully. And I won't say it's the first paper to do that, but it's a very influential paper which came out in 2015-16. So this was trained to work on Atari games. Okay, so for an Atari game, so it's like you have 18 state spaces in an Atari game setup. You have 18 states, and in that particular paper, it was trained uh, to play some 60 different Atari games which are available. And turns out the DQN model was able to outperform and beat a human player in around 41 or 42 games out of the 60 games on which it was tested on. Okay. So this was a significant step that happened in this part. More so that DQN paper got published in Nature also, because typically papers in computer science don't get accepted to Nature that easily. But since the results were so astounding or so important, this was published in Nature in 2015. You can go ahead and take a look at this paper if you want. Uh, yeah, what I was saying. DQN. Oh, I forgot what I was supposed to say before this. Yeah, sorry. So, DQN, one big caveat for DQN is that no matter what the state is, the number of actions needs to be discrete. So, if I have, let's say this is K, so my action should be a discrete quantity A of K, right? So, this DQN doesn't deal with that particular case wherein the actions could be continuous. So, DQN specifically deals with a discrete action space. One way, one improvement over DQN, not improvement, I would say, or uh, a way in which continuous actions could also be taken into account was introduced in a new algorithm known as DDPG. DDPG is DDPG is deep deterministic policy gradients. Okay, so this is essentially DQN, but for a continuous action space. So again, you pass in a state, okay, through some network, and you get what? Now this is the question. What should be the output for this neural network? For a continuous action space, I could define, if I had k such k available actions, I could define k q functions. Okay, since this is a continuous action space, what should be the output of this network? Any idea or any guesses? How a neural network, make it more general, how does a neural network deal with a continuous action space? I should remove DDPG because DDPG has some other properties. So let's say I'll just call it a normal neural network for a continuous action space. Any idea? Okay, I'll tell. So it typically employs two outputs. One is the mu and the other is the sigma. Okay, these are the two estimates that such kind of neural networks output. And from this, I define a Gaussian distribution and I sample my AIs with respect to that Gaussian distribution. So since it's a continuous action space, I get the corresponding distribution parameters, which is the mu and the sigma. From the mu and sigma, I define a Gaussian distribution and I sample actions from that. Okay, so that also takes care of the uh, exploration part because it's a probability distribution. The I need not always sample from the highest probability. I mean, sampling from the best possible action will always have the highest probability, but there is always a possibility of me taking actions which are at the tail end of the distribution. Okay, so this is how typically one deals with a continuous action space. Okay, uh, what else? Should I start with DQN or should I go to the policy? Let me just stick to what the lecture contains. Okay, so I next go for policy gradient algorithms. So far we have been looking at value function based algorithms and how different ways we can show the convergence for a value function based methods. And since the bandit uh, algorithms we have looked in the first 2-3 weeks, there has been only one mention of a policy gradient based methods. So we'll come back to the policy gradient based method and see how this also helps us. Okay. So certain advantages policy gradient methods offer. First is that it offers a compact representation, because eventually I am interested in getting a policy out. Okay. Value function is a way of evaluating or estimating the goodness of a particular state or a particular action. Okay. Based on that, I recover the policy by being greedy with respect to the value function. Here, in this case, if I directly work with the policy space instead of the value space, whatever updates I have will be update. The updates will be directly applied on the policy space. Okay, so it's a compact representation. Second is that it gives a better convergence behavior. Okay, so what happens is you typically parameterize your policy. So your policy that you parameterize by theta. Okay, and if you remember the policy gradient that we did in week 3, there was a performance measure, okay, for a policy which is typically the expected reward function. So for the bandit case, the performance measure looks like this. So it's eta theta is equal to sigma a q star of a pi of a given theta. Okay, and similarly we define the gradient for this eta theta as 1 by n. Okay, no. So approximation, right? So it's an estimate. So eta theta hat, the gradient of eta theta hat is 1 by n sigma I goes from 1 to n. This is Ri, the gradient with respect to theta pi ai comma theta divided by pi ai comma theta. Okay, so this is how it looks. Now, in order to take this idea and apply it to the full RL problem, okay, one thing is that my policy pi earlier was just a function of the action A. So here it will have the notion of a state as well. Secondly, my Ri, my reward will be replaced by the return. Okay, di of s. So if I take this into consideration, my uh, the gradient of eta hat theta looks like 1 by n. This is the return starting from state s naught, and instead of pi, I just put the probability of seeing that state at the ith sample state. Okay, so this is pi s naught parameterized by theta. Here, my gi of s naught is the return of ith sample starting from s naught and my pi of s naught theta is the probability of seeing ith sample starting from S naught. Okay, so this is how it looks. And uh, if I take this particular quantity, pi S naught theta by pi S naught theta, so I can represent it as the derivative of ln of pi S naught theta. So the advantage of this ln representation is that my product gets can be represented by a summation. Okay. So if I had to take a product of the different PIs, okay, so it's the first sample, second sample, and so on, all different products. Once I represent it in the ln representation, the product gets converted to a summation. So I have a summation over starting from P S naught. So I have P of S naught times pi of A1 given S naught, sorry, A naught given S naught, then I take probability of going to state S1 given A naught S naught and so on. Okay. So those summation gets converted into that particular value, and all the probabilities, since I am assuming that my sample trajectory starts from S naught and has an end. Okay. Assuming that the trajectory ends. So the summation over all the probabilities over there simply sums up to 1. Okay. So remaining the pi's that I have can be represented as j equal to 0, t minus 1. Just take the, again, go back to the original without log representation. Theta divided by pi of sj aj theta. Okay. So the simple unrolling of this ln pi should get you to this expression over here. Okay. Now, yeah. Now, if I were to look at this particular equation, uh, just a sec. Yeah, let me just first highlight this important equation here. Okay. Now, similar to how we were evaluating a particular state or a particular state action pair, now we'll define a new metric to define to evaluate the value of a policy. Okay. So we'll call it as rho of pi, which is defined as the value of a policy. So given a full trajectory, I want to evaluate that, and it should tell me how good or how bad that particular policy is. So in this case, let's say we say my rho pi of s is equal to rho pi for all s, which is for all s, this is stationary. And this one can define as limit as n tends to infinity, simply the average reward formulation. All the separate rewards that you get on following that particular trajectory, you simply average that without having any discount parameter. Okay, so we are looking at an average RL reward setting over here. Okay, so from here, maybe we'll, sorry, yeah, we'll look at actor critic method. Okay, so for that we go back to the reinforce algorithm. Okay, So we had discussed this in week 3, the reinforce algorithm. For this particular algorithm, my update rule looks like my delta theta is equal to alpha n Rn minus Bn times dou by dou theta of ln pi. Okay, this is for the bandit case. Okay, this is the reinforce update rule. From here, I would like to go to the full RL problem. Okay, so to go to the full RL problem, first of all, my pi would be dependent on a state. There is a notion of a state that will be introduced. Second, my reward gets converted to returns. So, so here the Bn is typically the reinforced baseline, right? And this Bn term is known as the reinforced baseline, and it's uh, somewhat of a heuristic measure to uh, determine whether the current reward that I have uh, is good or bad. Based on that, the policy gets updated in the positive or the negative direction. Okay, based on the reinforced baseline. One popular method is you just take the average of all the rewards encountered so far. That's your BN metric. If the current reward that you have is better than the average, you take a step in the positive direction. If it's worse than the average maintained so far, you take a step in the negative direction. Okay, so when you take it into the full RL problem, so you have this is converted to Gn of s, and my Bn gets converted to Bn of s. Okay, so Bn of s here tells me is what? Here BNFS tells me is what BNS tells me here is we start from state S, get the average of all the rewards that you have encountered so far. Okay. So based on this particular definition, my Bn of S is nothing but the value function representation. Okay. So this can simply I can replace it here. So my this quantity here is simply Vn of Sn. This is Sn, this is alpha n, and I still have the d by d theta of ln pi a n theta n. Okay. So now notice in the policy gradient method, there again comes the occurrence of a value function. Just move it here somewhere. Okay. So here there is an occurrence of the value function when I'm making an update for the policies. Okay. So typically one calls the policy update to be an actor, and this value function could be termed as the critic. Critic evaluates a particular state. The actor takes action based on the evaluation that the critic provides. Okay. Again, if I open up this equation further, so I get this quantity times alpha n. So GT or GN that I have, instead of taking a Monte Carlo update, if I write it down in terms of the one-step update rule, so this is Rn plus 1 plus gamma times Vn Sn plus 1 minus Vn of Sn times you still have the d by d theta ln pi. Okay, here your policy pi should have the state also. It's Sn An parameterized on theta n. You have Sn An parameterized on theta n, right? The bracket gets closed here. And turns out this is nothing but the TD error, right? This quantity inside the bracket is the TD error, which is also defined by this quantity. Finally, my reinforced baseline looks as follows. Okay, you might see that we are reaching closer and closer to the original value function update rule. Only one changes here needs to be done. Somehow, this d by d theta term, I need to define a policy pi in such a way that whatever policy that I have gets parameterized to either a 0 or 1 condition. If a particular state action pair is encountered, you get this to be 1, otherwise you get to be 0. Okay, some kind of a representation that you can get. So you define it as this quantity times alpha n dt, and let's say this is the phi representation, okay, for that policy. Okay, so this is how the update rule for an actor critic method looks like. Okay, from here, we are updating both the value function and the theta update in the same part. Okay, how? Inside the dd term, there is a value function which is there. The way the value function is updated is if a particular state action pair is encountered, then we update the theta for that particular state action pair because the policy is parameterized on the state action pair. Regardless, the states get evaluated even if that particular action is not encountered. So the policy gets updated for the state action pair, and the value function gets updated for all occurrence of that particular state. Okay. So even if that a particular action is not getting if a particular action is not getting encountered, the value function still gets updated, but theta updates happen on the state action pair. Okay. So this is the generic idea behind this. Now, if we continue with the reinforce algorithm, let me see how far we are. Okay, so we just continue with the reinforce algorithm. Okay, so here, let's say for the reinforce algorithm, if we go back to the original definition, so my theta updates are simply alpha times the derivative over the evaluation metric. Okay, so this evaluation here is a rho for the average RL definition that we saw. In the original reinforced paper, it was the eta theta metric. Okay, so here I defined my theta update to be alpha times d rho by d theta, where my rho of pi or rho pi is simply the limit as n tends to infinity 1 by n times expectation of, I'll just take the sum over, I've taken 1 by n outside, so it's just the sum over all the rewards, the expectation over that, given I'm following policy pi. Okay, this can be represented as the number of times state S has been encountered, the probability of encountering state S, the probability of taking action A given state S, and finally the corresponding state action reward then one can achieve. Okay, so in this case, my reward is simply marginalized over S prime. Okay, so it is summed over S prime. So I have this quantity times E are given as A. Okay. It's marginalized sum over S prime, right? Now, we'll next up look at something called as the policy gradient theorem. Okay, so this should be done in the next 20 minutes, hopefully. So for a policy gradient theorem, okay, let me take it to the next slide as well. Okay, let's see. Okay, so for policy gradient theorem, I start with an arbitrary definition of q pi. Okay, how it comes, I don't know yet, but I'll just define it as this quantity. This is expectation of RT minus rho pi. Okay, given initial state, given S naught is S, A naught is A, and following policy pi. Okay, this is the definition for q pi S of A that I start off with. Now, if I take the derivative of d rho by d theta, okay, this is again coming from the reinforced basic uh, update rule. Okay, so if I want to compute d rho by d theta, so since I have defined rho here, I just differentiate it with respect to theta. So I get sum over all state d pi of s, okay, summed over all a d pi by d theta. This is s given a times q pi s comma a. Okay, now here we'll say that our v pi of s is equal to a times pi. This is something we had seen earlier also. V pi is simply pi times q pi s comma a. This is not part of the derivation, but something from earlier knowledge that we had. So this is extra, okay, not part. We'll refer to this when we do the derivation, right? So now from here, if I make take the derivative of v pi s, I get d by d theta sum over all the actions pi s comma a q pi of s comma a, right? Now you apply the chain rule. So that looks like you have d pi by d theta. This is defined on s comma a times q pi s comma a plus I have pi s comma a d by d theta of q pi s comma a. Okay, this is the chain rule. Now, since I have defined q pi s of a here, I'll just take the derivative of that. Okay, so continuing here, let me copy this. Okay, and paste it here. Let's see. Okay, my equal to sign goes here. I remove this term. So basically, I need to take the derivative of uh, q pi s of a, right? So I say I take pi s a, this same as before. Now I just differentiate this with respect to the definition earlier that we had. This is r of s comma a minus rho pi of s. Okay, so this is for the first initial state, and later on we behave according to policy pi, right? So we have p s prime given s comma a given s comma a times v pi of s prime. Okay, this is just unrolling the definition of the q function. For the first action you take for first action you take as per the action which is given, and thereafter we follow policy pi, right? Okay, big bracket close. What now? Okay. Mm, again, copy the entire line. Take it here. Let's see. So what we are left with is the original this quantity minus dou rho by dou theta, because RAS becomes 0 when we differentiate it with respect to theta, plus s prime times p s prime given s comma a and d by d theta of v pi of s prime. Okay, so yeah, on the left hand side also it was d by d theta of v pi s. Okay, once I have that, I just take d rho by d theta on the left hand side and take everything else on the right hand side. So I have d rho by d theta, d rho by d theta is equal to, let's see what could be there. This whole quantity. Okay, d by d theta of pi s comma a q pi of s comma a plus pi s comma a, correct? d by d theta of v pi of s prime, the whole thing minus d by d theta of vs prime, v pi s prime. Sorry, not s prime. So vs. Okay, this is vs. Okay, to make it or to represent it in a even more compact fashion, what we'll do is let's first separate this out. Now we have sigma s d pi s over rho pi. Okay. Since the rho, sorry, this is the d by d theta of rho pi. Okay. Since this rho pi is consistent or constant across all the states, so on the LHS, this summation d pi s becomes 1 simply, right? So what we have is, I'm just substituting here. Whatever we have mentioned here, we just substitute it here. So this is d pi s. I get sum over all a's. I have d pi s comma a by d theta, q pi s comma a. Okay, this is the first term, plus second term is summation over s d pi of s, sum over all a. I have pi s comma a. This is summed over all s prime. I have the transition probabilities times d v pi s prime pi d theta, right? Minus the final term is simply sum over all s d pi s d by d theta of v pi s, right? Now, if I just take a look at the second equation, the second term in the equation, okay, I'll copy the second term here, copy, paste. So if I look at this particular term, this I can write it as summation over s, summation over a, summation over s prime. I have d pi of s, I have pi of s comma a, I have pi s prime given s comma a, and then remaining d pi vs prime given d theta. Now the good thing about this particular step is, since my steady state distribution is consistent or remains constant throughout, so any operation of the sum over any operation of pi s or the transition probability doesn't change the steady state distribution. So if my pi of s comma a and p of s prime given s comma a is operated on d pi of s, if I sum it over all the a's and the s's for the pi's and the transition probabilities, I'll still end up with a d pi. This is the property for a steady state distribution. So this will simply become d pi of s prime times dv pi on s prime by d dou theta, right? Now, meaning this quantity and this quantity cancels out, different color. So these two quantities cancel out, and what I'm left with is this big equation. Okay, so only the first term remains, and since the this summation is also equal to 1, okay, so the final equation that I end up getting is d rho by d theta, dou rho by dou theta operated on pi is equal to only the first term, just sum over all s d pi of s. This is the steady state distribution, a times d pi by d theta s comma a, q pi of s comma a. Okay, so this is the policy gradient theorem or the policy gradient equation. Okay, let me not write anything here as of yet. Let's color it. Okay, so you simply substitute this entire quantity into the reinforced equation that we had seen 2 3 slides ago, and you will again obtain the same equation. Okay, now when we work with policy gradient and function approximation, this is policy gradient plus function approximation. So typically here we define some function s comma a which should be the estimate for my q pi s comma a here in this case. Okay, now here one I would like to minimize the uh, error, okay, between these two functions. So I have q pi s comma a minus f w s comma a. Okay, so this is my mean squared error which I would like to minimize so that the function that I have, the function approximation, should be as low as possible. Okay. Now, if I just take a derivative, if I take the derivative of this whole quantity, then what I'll get is simply uh, the 2 vanishes. I have q pi s comma a minus fw s comma a times d by dw of fw s comma a. Okay. Now, I want to show the consistency for this particular equation. So this thing, this particular derivative should satisfy this equation in order to show the convergence of the value function, right? So it should satisfy this consistency equation, which is, mhm. So if I sum it over all the steady states, okay, and sum it over all possible, uh, sorry, if I sum it over all the steady states and take this quantity, so my error between the predicted and the original value should be low such that it becomes eventually reaches 0. Okay, so the theorem here goes as such. Let's say we term it equation number 4. Okay, so the theorem here states that if fw satisfies equation 4 and I say that my dy dw of fw s comma a is simply this quantity here. I simply define this to be this particular quantity such that if I put this into the consistency equation over here, if I put that this quantity instead of fs uh, d by dw of f ws comma a. So first the pi gets cancelled, and whatever I have I obtain would simply be the d phi by d theta. Okay. So once I simply substitute this quantity, let me, since this is a theorem, this is a pink. Okay. And finally, then my d rho by d theta becomes s d pi of s summed over all a's dou pi by dou theta s comma a hence fw s comma a. Okay. So again, we get equivalence to this blue equation. So I'll again color this blue. But notice that in both such cases, the only difference is the representation of the q pi. So here, instead of having the original q pi from the lookup table that we get, we have successfully been able to approximate it by the function fw s comma a by making sure that my dou f by dou w is this equation and that fw satisfies this quantity. So once we show that, this shows the convergence of the policy gradient approach along with function approximation, right? So with function approximation, this method shows how policy shows that policy shows the convergence for a policy gradient method. Okay. And what else? What else? Right. So let's say now if I define my pi of s comma a to be the softmax policy, simply the softmax policy. So this is how softmax looks like, right? SP. Okay. So if this is how if I simply put this into the equation, so finally my dou by dou w of fws comma a looks like this quantity. It's just a matter of substituting it there, and we get times phi sb. From here, if we know the derivative of fw, so one way to recover the fw would be to just take the linear uh, representation, right? So if I define it as this quantity, okay, so this could be an appropriate function approximation for the q function. Okay. And finally, if I take the mean of this quantity, if I take the mean of function approximator, or as also called as the feature vector, if I just simply take the mean of this quantity, sum over all the actions given, f omega comma a pi of s comma a, this quantity goes to 0. Okay, you can see it if you just substitute this value over here. You see that this entire equation goes to 0. That means whatever function approximation that I'm making, so the phi values that I have taken, half of the time would be above the average value of the sum over all the phi's, and half the time it would be below. So it's like a mean zero based function approximator that we are taking. So yeah, the distribution of the uh, phi's or the distribution of the states would be above the zero mean. Okay. So with this, we conclude the discussion session for week 9. If you have any questions, you can stay back. Otherwise, I am done with what I had to cover for today. Any questions so far? No, right? Okay. Fine then. Thank you for coming. With this, we can end the discussion session for week 9. Okay. Thanks for joining. I'll see you next week. Next week, we'll start with the hierarchical RL thing. And preferably, my intention is I would try to focus more on the implementation part of deep RL techniques. Okay. This is what my plan is. Let's see how it goes. Okay. Thank you for coming. Bye. I'll stop the recording.